You say you're starting to get this? Well, I have great news. Then let's make it harder. Huzzah! We're gonna look at a two-body force diagram problem. In this clip, Snoopy is being pulled down by a much larger dog, and Snoopy is 15 kilograms while the larger dog is 30 kilograms. Now, let's pretend that the ice is so slippery here that it's frictionless. And this might sound like a problem in your physics class by now. Because of the logic of cartoons, this rope is not even against the ice edge, so maybe I'll just place a pulley here. I bet by now you recognize this from one of your physics lab's problems. If not, it helps to draw a sketch. Okay, clicker doesn't work sometimes. That's good to know. Well, let's try to find the acceleration of these blocks. I mean dogs. Sketch. You know. Okay, yeah. First, let's identify the system. We have two systems in this case. One is Snoopy, and the other is the big dog. So I labeled them S and B. And let's begin a force diagram for them. And there it is, as you can see. We have a normal force, gravitational force, and gravitational force. Now we have to put a coordinate axis. And it's important to realize that the tension along the wire has to be one consistent direction. So this is actually how our coordinate axis is going to show. Am I going too fast? I think you guys are good. So let's go into some algebra. The horizontal force for Snoopy is as follows. The only force in the horizontal direction, because there's no friction, is T, and that'll equal ma, mass of Snoopy. And then for the vertical forces, for the big dog, we have mg minus T equaling ma. Now, in solving this, you'll find that eventually you'll have to substitute T for the mass of Snoopy times A. And this is where, because you have to substitute, you might want to have subscripts by your m's so you don't get them confused. It just helps to label everything, you know? Oh, and your final answer should be 6.53, before I forget. Now, there is still one more thing we need to cover, Charlie Brown, and that's the coefficient of friction. Friction is caused by the amount of forces that press two surfaces together, and the characteristics of those two surfaces. And when you think about that, that makes sense. Because you have a normal force, but then you also have this little mu thing. We'll get into that later. Let us go over two terms. Kinetic friction. This is the idea that surfaces sliding past each other have one value of friction, and that static friction occurring before the slide has another value. You can see it mathematically illustrated here, where as someone applies force to an object, the object also applies that much force back to them, until the object is actually in motion, and then there's an actual constant of kinetic friction. And these are the formulas, which we label the coefficient of friction with a mu, which is actually really hard to type on the computer. It's really annoying. And obviously, they might not look as Egyptian or like crocodile teeth, but one thing's for certain, they sure are fun. Fun. Now, I have another cartoon of Charlie Brown to illustrate the example of static friction. This is Snoopy, and you can see that there is so much friction between the snow here and the sled that he is still unable to exert the amount of force necessary to push it. However, I think Charlie Brown seems to be doing just fine, and you can see this is an example of kinetic friction, because this is friction occurring while the sled is sliding. That was a good cartoon. So last question today, Charlie Brown. Oopsies. You didn't see that. Okay. Last question today, Charlie. Let's say that Snoopy is sledding off a 45-degree angle, because why not? Yet apparently, he is not moving down, somehow. Until Charlie Brown, of course, helps him along. So if he's not in motion, what must the static coefficient of friction be in this case? Well, let's add a force diagram, and luckily for me, I don't have to draw a sketch. I just figured I should put the arrows right on the illustration. However, it helps you take a moment and pause, and you can draw a sketch right now with your force diagram. We have one gravitational force, which I had to break into components, just like we always do. We have a friction, and we have a normal. It should be reviewed to know that this 45-degree angle here, which was given in the problem, is the same as the one here. I like this song. Okay, so now let's get into some of the algebra part. We take Newton's second law, and we look at the horizontal and the vertical. With the horizontal, we're dealing with the friction. We're dealing with mg sine 45, and then it equals ma. However, because there's no acceleration currently, we are at rest. A is 0, so therefore this whole thing is set equal to 0. And from our equation of fun, we can set f equal to un. Meanwhile, with the vertical, we have n minus mg cosine 25 equaling 0, or n equals mg cosine 25. And perhaps by now you already realize what we have to do is substitute. Yay! Yay! Okay, so in this case what we have to do is substitute n of mg cosine 45 into this equation here, as I did below. And eventually, the cool thing about this is the masses should cancel out, so you don't even have to know how heavy Snoopy and his sled is. It is interesting. I know you're interested. Oh, Charlie Brown says thank you, narrator. Well, we went through Newton's second law of motion, gone through what each term means, with a step-by-step procedure on solving unbalanced problems, including pulley problems. And lastly, we looked at types of friction forces and an example of how they are calculated. You still have one more question, don't you, Charlie Brown? That probably is who I am. Well, I'm just gonna let that be a secret. For now.